Hello the internet and welcome back to my channel. On the bench today we have a pretty interesting power supply. This is an XP Power power supply. It belongs to the Flex Power series. This power supply has reached my desk because its fault is broken. I have no idea what's wrong with it, but on this video we're gonna try and see if we can fix it. I understand that this one is pretty expensive. It's a pretty powerful power supply. I think in total, as is configured, it's about 600 watts, so it's a bit more worth looking into it. Now, quick disclaimer, there are very high voltages inside power supplies, even when they are unplugged. They can be lethal, so this is not a tutorial. I discourage you from trying and opening a power supply and trying to fix it. If you decide to do so, you do at your own risk. Now, the special thing about this power supply is that it's modular. You can basically go online on the XP Power website and you can choose what kind of chassis you want, so how many modules you want, how many outputs, what kind of power you want from each one of those outputs. This power supply is the X7 chassis, and I understand that we have 3 power modules and 1 fan control. So that's the fan control module, which is telling the device which is connected to whether the fan is working or not. This is a 24 volts output modules, and these are 2 12 volts output modules which happen to be bridged together. So let me thank today's sponsor PCBWay, and then I guess we can remove this label, remove the lid and take a look inside. I'm quite curious because it's a pretty interesting piece of hardware. Oh wow. Alright, so this is quite interesting. So the power supply is divided into 2 blocks, as I was expecting. We got mains coming here, and this is some sort of a primary section. And from this primary section you have these black connectors here. And the black connectors are basically the connectors for the modules. These are the 2 12 volts modules. They're upside down, and you can see the connections for the, let's call them the motherboard, the primary section, I'm not sure. These are bridged together on this power supply, but they can operate independently, I understand. And the one I've opened here, this is the 24 volts module, and it's quite interesting because there's really not much happening here. The fact that I have these very small terminals coming from the main section is telling me that there's relatively high voltage coming in, because it means that there's a very low current, I suppose. And then these are just DC to DC converters, and this is just the fan control board. That's where the main fan, which is sitting here, was connected. Again, it's connected to the motherboard, and it also has a little output control. It says fan control here, which is telling the main device where this power supply lives whether the fan is working or not. Now the good news is that I don't see anything exploded. Maybe before I even test it, I want to make sure there are no shorts on the main, let's call it the main section. I don't even know how to call it. Remove this board from the plate here and just make sure that the main transistors, the main semiconductors, are not completely shorted. Oh my gosh, no. Moo. And unfortunately I was mistaken, and the power supply did go bang, and we have a big problem here because there is a component here that's maybe some sort of controller or whatever. It's completely destroyed, and I have no idea what that component is. Obviously there are no schematics for this power supply, and I haven't got another one to find out what component is that one. But it's a big aftermath. I see, if I'm not mistaken, I see there's a completely destroyed burned trace here. So unfortunately this is a no fix, 100%, but nothing is stopping us from, you know, taking a peek and see what happened on that massive aftermath that we have here. Alright, there is a little plot twist. Look at that, I found the missing piece. So we now know what that component is, and I have a feeling that all these black stuff, it's kind of superficial, so maybe we do have a chance of fixing this power supply. But yeah, that's completely destroyed. It exploded from inside. The trace used to be here, evaporized itself. Look at that, all this bit used to be a trace. So that's the other side. So the trace in between has completely vaporized. Let's give it a clean and see what's left behind. Alright, it's been a few days since the previous segment. Meanwhile, I got a cold, so hopefully my voice is not too bad. Now, cleaning the PCB has got very good results, so I can finally see what's going on here. I've been studying the PCB a little bit, but I think I start understanding what's going on here. Mains is coming through here, and it's going through a couple of fuses, which are both completely open. And then we have some filtering stuff in here. And eventually we are going to a bridge rectifier. The AC is coming on the inside pins, so this is one of the main legs. And that's the other one. Now the bridge rectifier is not shorted. I tested it, I don't see any shorts. I see the semiconductors, I see the diodes, but there is no shorts anywhere. And we got the positive coming out from this pin here and the negative coming out of this one. This is not a complete switch and power supply, it's just a section of it, because it's a modular power supply. So the role of this board, as I understand, is to generate that DC voltage, 390 volts DC voltage, and that's it. And then that would be passed to those other modules. The modules will then do the chopping and generate the low voltage DC, like 12 volts, 5 volts, 24 volts, and so on and so forth. So there's really not much happening on this board. What I see is that from the positive output of the bridge rectifier, the voltage is going to this pin here. And this is an NTC, it's a thermistor, so it basically prevents the power supply from drawing too much current when it's being plugged in. Otherwise, these big electrolytic capacitors, which we'll see in a minute, will just draw quite a lot of current, which is not great for your electrical system. From the NTC, that positive DC voltage is going here, which is then linked to this pin here, and I believe this is a big diode, and from the other side of the diode is basically going to the positive of the electrolytic capacitors. Now, from the electrolytic capacitors, the voltage is going straight to the modules, and the modules are connected to this board with this connector. It's made of 12 pins, and I understand that 6 pins are for this DC, high DC voltage delivery. The other ones are probably for control. I can see that the positive of the electrolytic capacitor is coming to these 2 pins here, and this one, while the negative is going to the other on the other side of the 6 pins connector. And that's it, more or less. At that point, these 390 volts DC is being sent to the modules. The modules will have their own controller, I'm guessing, and the MOSFETs and the transformers and the inductors to actually chop off this DC voltage and generate the low voltage required. So if this board is so simple, what about the rest of the components? Now, we have some transistors here. I believe they're MOSFETs. They're attached to the heatsink, and it's a L498-1AD, and it's a power factor controller. So this power supply has power factor correction, of course, and that's what happens on this side of the board. Now, I don't have the power factor correction too clear in my mind myself, so I'm not in position to explain you what happens, but I know it happens here. I know we have some MOSFETs here, we have a controller here, and this chip here, it's TC1413NE, which is a MOSFET gate driver, and I'm assuming that they're all linked together, and this is for the power factor correction, basically. Now, when I went to check the MOSFETs for the power factor, I thought they were fine, though on some pins I'm getting like a healthy reading, like here, 0.5 volts, but on some other pins I'm getting this. Now, I thought, well, maybe this is normal, so I went into resistance mode, and this is reading 14 ohms, which is, it's not that short, so I thought maybe that's totally fine. But let's put a little question mark on that section, and we'll come back to that in a minute. Now let's get to the elephant in the room, this big component with the lid missing. So obviously something happened there. It's a TOP246GN. It's an offline controller. What does that mean? It basically feeds off the line, not because it's offline or online, and it's basically a small switching power supply integrated in one chip. What that means is it has MOSFETs inside and the controller, and it only needs a little transformer and some extra components around to actually generate a low voltage DC. Now, this chip here could actually be used as a main controller, a main and only component on a very small switching mode power supply, let's say 20 watts, to generate an output. In this case, I think this is used to generate the 5 volt standby that the datasheet says that this power supply has out of this controller here.
Now, there is a big question mark though. Now, this controller has the MOSFETs inside, but most importantly, well, it needs a transformer, because without the transformer, it can't chop anything. You need a transformer in order to do that, and one of those yellow things, and the only place where I can see a transformer on this board, and there's nothing under the heatsinks, is here. Hopefully you can see there is a little yellow transformer here, and I'm not sure how much you can see that, but there are some small wires coming out of the transformer and going back to the PCB. Now, these 4 wires are connected to this section here, which happens to be the section where one of the traces basically disappeared, vaporized. These 2 pins is definitely one of the lines going inside the transformer. It's a coil, so obviously it reads the short, and on one end, this is directly connected to the plus of the electrolytic capacitor, so basically the 390 volts output of the power supply itself. So we got 390 volts going through the little transformer, back to the PCB through the broken trace, and then into these IC, because this is basically connected through these components here, this big trace here, and then into this leg of the controller here. So what must have happened is that this component shorted to ground, and when that happened, it basically shorted the 340 volts coming out of the, let's call it the output of this section of the power supply, through the transformer, through these little wires, through the traces on the PCB to ground. So the first one to go was the trace itself. It just vaporized. It couldn't deal with the amount of current. Then the fuses and the IC itself, it just blew up completely. So obviously the first step would be to replace this component. I have some spares, we'll get to that in a minute, but obviously I'm concerned of maybe some other components being affected by this failure nearby. We have 2 diodes here, 1 resistor, and what I thought was a inductor, but I actually think is a capacitor. Now I think this is part of this snubbing network. It's basically a little system designed to absorb the huge amount of voltage which comes out of a transformer when the switcher controller, in this case this IC, opens up. So the magnetic field inside the transformer, while it's collapsing, is generating a voltage. This voltage has to go somewhere, and if the switcher is open, you end up with like 1,000 volts on the circuit, which eventually will destroy components. So there is a number of small components like diodes and capacitors and resistors, which are basically there just to dissipate this very high voltage, designed to deal with these high voltages, so that the high voltage is not destroying or damaging any other component. Now these 2 components here are 2 diodes, and they do read as diodes, even though I think they are in parallel, maybe not, but anyways, they don't read like a short. And these components here is a resistor. It says 6812, and it's reading 68 kilo ohms, so that seems to be working totally fine. Now, I thought that that was maybe an inductor, and maybe it was open because it's reading the resistance which is parallel to it, but maybe not, and we'll see that in a minute. But definitely this is not reading as an inductor, and if it's a capacitor, unfortunately I would probably need to take it off the board to properly measure it. Now, this section of the board is quite interesting because I see quite a lot of wires coming from this section here, and I have these 1, 2, 3, 4, 5 components, 5 diodes, which seem to be connected to these wires. I have a feeling that this is the voltage feedback coming from the output modules, so that the power supply is somehow able to confirm that the modules are working, that the voltages are fine, and everything is as expected. So I think the next step would be to definitely replace this blown component, but I need to find out definitely about this, what I think is now a capacitor. And I was a bit stuck, there's no marking on it, there's absolutely nothing. So little plot twist, I managed to acquire another identical power supply. This is also faulty, so I can't take this as a complete reference, but at least it's not blown up. So on this new PCB, I could definitely confirm that this is not an inductor, and I think what I want to do is to remove this capacitor and measure it, and then I'll remove the capacitor on the other board, I'll measure it as well to make sure it works, and then I'll replace the blown component. I'd like to see whether this thing is actually starting and, I guess, generating 5 volts out of this connector through this component here. Now remember, we had a little question mark about the MOSFETs a minute ago, and the thing is, I've realized that if I'm measuring the MOSFETs here, I'm actually reading 0.98 volts, and if I'm measuring here, I actually think it's these 2 here, I've got 0.487. But going back to the damaged board, if I'm measuring exactly the same points, now I'm getting a short here, and if I'm measuring this 2, I'm also getting a short. So let me begin with this section here. I've removed this component, I've removed the capacitors on both boards, and then I think I'll remove the PCB, the heatsink, the MOSFETs. We'll meet again at the end and we'll start taking some measurements and we'll decide what to do then.
And let me quickly thank the sponsor of this video, PCBWay. Whether you need a PCB, a 3D print, metal sheet fabrication or CNC machining, well, PCBWay can help you with all your projects. If you follow my channel, you know I've been using PCBWay for all my projects for quite some time, and I've always been happy with both the PCBs and the 3D prints that I've got from PCBWay. And there is plenty of free projects online you can use to place an order at PCBWay, so you don't need to be a PCB designer. And the process is extremely easy. Just go on PCBWay.com, upload the Gerber file of the project of your choice, and then the process is more or less automatic. Select a postal service and PCBWay will deliver the PCBs at your place. Take a look at PCBWay.com, the link is also down below in the description, and let me thank PCBWay for sponsoring my videos on my channels, because their help makes this video possible. So thank you very much, PCBWay. Now let's continue with this power supply.
Let's begin with the simple stuff, these two capacitors. If I'm measuring the good one, my Fluke is reading 9 nanofarad. It's quite a big capacitor, I guess it's probably rated for quite a few volts. Let's check the bad one. And it's reading 10 nanofarad, so it looks like it has survived. So maybe we can temporarily reuse it for tests. Obviously, eventually I want to replace it. Now, when it comes to the MOSFET, it seems like they're fine, because now I cannot see a short anymore. And I believe this one is supposed to be a diode, so it looks totally fine. Now, let's quickly patch it up through the component tester and make sure they actually test okay. And the first MOSFET tests totally fine. Let's check the other one. And the second MOSFET is also fine, which is probably good news because I'm assuming that those can be expensive. So unfortunately, or fortunately, depending on the point of view, the short is on the PCB. Now, if I'm looking at the good board, I basically have the middle pin is the supply voltage, which is coming from the positive of my bridge rectifier here. The pin on the left is the negative from the supply here. The pin on the right is the gate, and the gate apparently is shorted to ground. And then suddenly I remember that we had a component on this PCB which is called the MOSFET gate driver, which is this component here or this component here. And looking at the schematics, it's basically a buffer to drive the MOSFETs. Don't ask me exactly why it's there. But this is, on the good board, is actually connected to the gate pin of the MOSFETs. It says 5 ohms because I think it's going through a resistor, and this obviously is not shorted to ground. Now, if I'm looking on the bad board, obviously I still have 5 ohms here, and obviously then I have 5 ohms, actually 14 ohms to ground, and this is where it becomes a bit complicated because you see a short to ground on these IC. Is it going to be these IC shorting to ground? I also have a short on these diode here. 10 ohms, is this causing a short? I don't know. I think I'd like to just remove some components one at a time and see what happens. I think I will start with the gate driver because if I'm not mistaken, the gates of this MOSFETs is going to the gate driver only. So if I have a short to ground, it's probably the gate driver internally shorted to ground. So let's take that off the board and then we'll check again and see if we still have a short. And the short has gone, so let's check on the actual IC here. So this component is definitely shorted. And I have some spares for the offline switcher. I haven't got spares for the MOSFET gate controller, so I'll borrow it from the other board. Then I'll rebuild that trace, reinstall the capacitor, and then I guess we can try and power this up and see what it does. And while I was cleaning the capacitor, I unintentionally damaged it because I didn't realize it's made of plastic. So I insisted a bit too much with my desoldering braid to remove the old solder, and the case melted. So I'll have to find some replacements. I guess meanwhile, for a test, we can use this one, which was still reading the correct value. But yeah, it's a shame that I damaged this one. Before I put the heatsink and the MOSFETs back, just a quick look underneath. There's really not much. I would say some capacitor, that's another capacitor. That's the NTC that I was talking about. We have a 0.5 ohm resistor, and under this coil, this inductor, I guess, that's the diode that I was talking about at some point. That's it. However, now you can clearly see those little wires that are coming through the PCB under these blob of silicon, and they're going into these little transformers. Now, to fix the fuses, just as a temporary test, I'm going to bridge them with the resistor leg. Now, don't do that unless you have protection beforehand. I'm going to use my current limiter to power this up. I will never power this up off main without the fuses. Fuses must be replaced with the correct values. Alright, I'm ready for a test. I got two multimeters here. The Kaiwitz is connected to basically the output of the module, so it should read something like 340 volts DC. The Fluke is connected to what I think is going to be the 5 volt standby. Now I've also wired what the manual calls global inhibit, which I think is the on-off button, but for now I'll just leave it there. I just want to make sure that nothing blows up. And we have, most importantly, the 5 volts DC standby, because that's coming from the IC that I've replaced. I'm going through my current limiter. It's set to pretty low current. I'm keeping my distance here. Let's give it a go and see what happens. In 3, 2, 1, go. No. Oh, okay. That's new. In 3, 2, 1, go. No. I'll check the footage. We definitely got some voltage out, but the component went up in smoke. And it's a new component. It's kind of weird. So I'll have to check and understand what happened. I had a quick look at the footage. The good news is that we had 5 volts for a split second, but we had 5 volts. But obviously we also had some magic smoke coming out of the board. Now the component that smoked is this, I think it's a diode, which doesn't read as short, it reads at 0.7 volts. One end is ground, the other end is basically on the line, which goes on the input of the MOSFET gate driver. And no, the MOSFETs are not shorted again, because they don't read as short here, and the input of the MOSFET driver with ground is not reading short, and it's not reading short with the output either. So the IC seems to be working. That being said, I can't be 100% sure that that IC is working because it comes from a faulty board. So who knows? But I guess I will have to study the circuit a bit more before I can come up with the next step. Alright, so I've been poking with the PCB for a little while, and I think I have a better understanding of what's going on. Now, the component which went up in smoke looks like a diode, and it's got H5 written on it. H5 seems to be a Zener diode, a 15 volts Zener diode. Now, on one end, this diode is on ground. On the other end, I believe it's connected to a 12 volts line. And how do I know that that's a 12 volts line? Well, first thing first, I got my multimeter in continuity mode. I've discovered that this line is basically going to the MOSFET gate driver here, pin number 1, which is the VCC of the gate driver. So that's basically the supply voltage for the gate driver. And it's also going to pin 19 of the power factor controller here, which once again is the VCC for the chip itself. So this seems to be like an auxiliary voltage for the little electronic that we have on this PCB. Now, going backwards, this line is going to these 2 pins here. Now, it's reading 10 ohms because there's a 10 ohm resistor here, but if I'm checking here, it actually says 0 ohm. It's going through a resistor, there's a diode in parallel, and these 2 pins here belong to a relay. I didn't realize that we had a relay on the PCB before. But I've removed the heatsink, and this orange thing is actually a 12 volts relay, and this is how I know that that's probably a 12 volts line. It must be around 12 volts, otherwise the relay just it's not going to work. Now, if I keep following this line, eventually it comes to these two joints here. And these are two of the four wires which come out of that yellow transformer on the other side of the board, the same transformer which is generating 5 volts standby. So what I think is happening on this board is that the offline switcher is directly connected to mains, and it starts running as soon as you plug it into mains, basically. This is driving the little transformer, and it's generating 5 volts standby on this connector here, but it's also generating 12 volts or something like 12 volts on these, let's call it auxiliary winding, which is then powering the electronic on the board. And I understand that the relay is basically there to supply the more or less 400 volts DC to the MOSFET. So I guess it's kind of like a main switch that only power the MOSFETs when the power factor corrector is actually being energized. And here comes our Zener diode, 15 volts Zener diode. It sounds like a protection for the line. So if the line is going for whatever reason over 15 volts, the Zener diode will just clamp the excess voltage to protect those two ICs basically. Now, considering that the MOSFET gate driver was shorted and that the Zener diode went up in smoke, well, that's telling me a couple of things. Number one, that probably also the power factor controller is gone, probably has been overpowered for whatever reason. And most importantly, that there's probably way more than 12 volts on this line for whatever reason. So my hope is that the Zener diode got damaged before, and when I applied power again, it just completely burned out. Because if that is not the case, that means that we have way more than 12 volts on that line. And if that is the case, I can only blame the transformer, which is really not something I can replace. So my next step would be to try and find out what kind of voltage we have on that line. And I don't want to do that with the multimeter. The multimeter is kind of slow. So I'm going to connect my oscilloscope using a differential probe. When you're dealing with power supplies, it's always a good idea not to have ground in the way. And basically give power to these things momentarily so that I can see where the voltage is going. So let me wire the oscilloscope, and we'll try and get an answer out of it and find out what's wrong with that 12 volts line. I've got the oscilloscope set in roll mode, so it's rolling from right to left, and on single capture, so it should stop as soon as the voltage reaches 7 volts. Now, I haven't reinstalled the MOSFETs for the power correction. It should be fine. It's just I don't want to keep installing and reinstalling, soldering, desoldering those MOSFETs, because eventually the pads will start falling apart. Okay, let's see what happens. 3, 2, 1, go. Nothing, because I haven't plugged anything, right? Of course. Okay, let's see what happens in 3, 2, 1, go. Right, according to my oscilloscope, the voltage went up to 13 volts. 13, more or less 13 volts, which I feel is probably totally fine. And I think for the first time I heard a very clear click. That was the relay basically triggering. Let me just try and power this up again, and maybe I'll keep it on for a little few more seconds and see if it stays on and the voltages are still stable and we're getting 5 volts here and there's any more smoke coming out of the board. 3, 2, 1, go. Okay, now I see smoke coming out of that thing, but that doesn't make sense because I got 13 volts. That shouldn't go up in smoke, so hopefully it's just a faulty Zener diode. And then I realized that there is another scenario that I might have not considered, which is that the Zener is actually doing its job. It's just clamping a much higher voltage coming from that 12 volts line, which is not 12 volts anymore, is whatever it is. And the Zener is just trying to keep it down at 215 volts as it's rated for. Now the question mark is that a 15 volts Zener diode should clamp around 15 volts. If you look at the datasheet, it says 14.25 volts is the minimum. So 13.26 with the Zener on fire, I don't know, it feels to be on the low side. Now I could remove the Zener diode and see what happens on that line, but my concern is that the line is going at stupid voltages and I'm instantly frying the gate driver and the power factor controller. But what I've done instead, I've ordered some replacement Zener diodes, 15 volts. I'm going to replace it, and if the Zener diode still goes up in smoke, well, then we know that we have a problem on the line. If it doesn't go up in smoke, well, then it means that that Zener diode is faulty. So let's wait for the delivery and see what happens. 15 volts Zener diodes have arrived. Before I go ahead and replace the one on the board, I'd like to quickly test the one on the board. So let's remove it and run a quick test. This is the Zener diode which was on the board. I wired it to my bench power supply. I've set a current limiter of 100 milliamps. I will start with 0 volts and go up and see if by any chance the Zener diode gets conductive before it gets to the minimum which we noticed on the data sheet that says 14.25. 3, 2, 1, go. And there's no current flowing. And let's slowly move the voltage up. And at 5 volts I'm reading 40 milliamps. I'm not entirely sure whether that's supposed to happen or not. Well, it's not scorching hot. So let's continue with our voltage. Let's go up a bit more. And yes, the Zener diode is getting scorching hot. So hopefully that is telling us that this Zener diode is actually faulty. Let me try with one of the Zener diodes which I purchased. And would you look at that, at 5 volts we have 0 milliamps running through the Zener as it should be. So we should see something around 14.25. There you can see we start seeing a little bit of current flowing at 14.67. So this is working exactly as expected. So let's replace it and see what happens. Alright, I know this is a little bit of spaghetti junction, but I got the Kaiwitz connected to the very output of the power supply. It should read something about 340 volts. The Fluke is connected to that 12 volts line, which is where the Zener is connected to. And this multimeter, which is very old, I think it's the very first one I've ever had. I bought it probably when I was a teenager, so many years ago. It's only connected to the 5 volt standby, you know, just to get some kind of a feedback that something is happening within this power supply. I'm going to wear my safety goggles. I'm gonna take a step back and we'll see what happens. Will I be able to release the magic smoke again from some components, or will it work? Let's give it a go. 3, 2, 1, go. Alright, would you believe it? It seems to be working. We got 326. Oh, something is smoking again. Oh, no, something is smoking. I think it's the gate driver, which is the one we replaced before, and it's smoking again. Oh no. But it was working. We had 13 point something volts, which is totally fine. I should probably check with the thermal camera, but I'm expecting the Zener to be fine. We had 5 volts, we have some outputs, but we also had some magic smoke again from a different component. So, more fun to come. I got the thermal camera out. This one is the gate driver, so that's what I thought it was smoking. Let's turn it on again and just confirm it. In 3, 2, 1, go. Yes, it's definitely that one. 199 degrees to 100, and it's smoking again. Now, unfortunately, I won't have a spare part this time, so I would definitely need to order new ones. But before I just replace it blindly, well, I need to understand why that happens. Now, this is a very simple IC. We got pin 1, which is the voltage, the supply voltage coming in. Pin 2 is the actual signal, which is then being used to drive the MOSFETs, and it's coming, I guess, from the main power factor controller here. Pin 3 is non-connected, pin 4 is ground, pin 5 is another ground, pin 6 and 7 is the output used to drive the MOSFETs, and pin 8 finally is another supply voltage which is linked to pin 1. Now, the first thing I'm noticing is that pin 1 and 8 are supposed to be linked for proper operation, the datasheet says, but actually they're not linked together. My multimeter is reading 60 ohms, so these are not actually linked together, but I remember when I removed the IC, the pin 1 and 3 are linked together, but pin 3 is not connected, so I'm not entirely sure whether there is a mistake with the PCB, because 1 should be connected to 8, not with 3, but this is definitely connected to pin 3. Now, for this thing to go at those temperatures, we must have a short. If I'm checking pin 1, which is the VDD, the voltage coming in, and ground, let's say I don't have a short. Let's check the other pin, which is not connected. I don't have a short. Do I have a short between the input pin and ground? We don't have a short. Do we have a short between the output pins and ground? That's one of the pins, and that should be the other. It should be connected internally. And that's it. That's no short either. So the thing is not shorted, but it's going to 200 degrees. I have only two ideas. The first one is that these IC was faulty on the other power supply. And maybe I've replaced a shorted IC with another one which is some sort of shorted, maybe it's only shorted when some voltage was being supplied. The other idea I have in mind is that the VDD, the voltage actually driving this component, is somehow completely off spec. Now, according to the datasheet, this component is expecting a supply voltage in between 4.5 and 16 volts, but we measured that line. That's the same line where the Zener diode was, and it was reading 13 point something, so that seems totally fine. Now, the last idea I have is that the input voltage is way too high. The datasheet says that the input voltage is basically in between VDD plus 0.3, so we're talking about 13.3 volts maximum, and as a minimum it can go 5 volts below ground. So I'm expecting something within that range. Maybe that's completely off spec, that's going to, I don't know, 100 volts, and that's obviously frying everything and shorting something inside. So let's measure those two pins and see what we get. I got those two beautiful Probe Masters grabbers connected to the IC. I'm expecting the same 13 point something volts that we were reading before. Power up in 3, 2, 1, go. Yeah, we are getting 13 point something, so that's definitely not our problem. Now let's try the input pin instead. 3, 2, 1, go. And what you see on the oscilloscope is the signal coming from the power factor controller, which is still alive apparently, which is good. Now the positive voltage of that signal is about 10 volts, which is below VDD, so that's totally fine. The negative is a bit more than minus 5 volts, but it's, you know, kind of spiky every now and then. Now, is that enough to cause those 200 degrees coming out of that chip literally instantly after power up? I really don't think so. So I think the next step is to order a new replacement for that component and swap it again, and hopefully that's going to be the last bad component on this power supply. Replacement components have arrived from DigiKey. Now, before I go ahead and swap it, let me send a big thank you to DJ Marek78. He's been my technical advisor behind this video. DJ Marek is very skilled when it comes to electronics and power supplies in particular. So thank you very much, DJ Marek78. And for all my Romanian followers, go and take a look at DJ Marek78's YouTube channel where he's doing repairs. So yeah, if you know the language, please take a look at this YouTube channel. And speaking of YouTube channels, if you like what you're seeing, don't forget to like this video, maybe subscribe, leave a comment. I'm on Patreon. There's a free tier on Patreon. If you don't want to support me financially, you can buy me a coffee as well. Sorry, I don't mean to waste your time, but you know, sometimes it takes so much time to make these videos, and sometimes not seeing much interaction from the viewers or even not seeing many views, it's a little bit demotivating. So, enough me talking, let's swap this component. I wired the, what we think is the faulty gate driver to VCC basically, VCC and ground through my bench power supply. Let's see if it gets scorching hot by itself or not. 3, 2, 1, go. Yeah, this is definitely getting hot. And this is limiting at 15. Well, now it's only 32 degrees because I'm limited. I'm assuming that if I'm turning this up a bit, yeah, this never stops. Well, I guess we're all waiting for this, right?
1.21 gigawatts. Great God!
Will it work? Well, I'm not optimistic, but let's find out. In 3, 2, 1, go. Okay. We only have 287 volts. Nothing is horribly on fire. And the hottest part of the PCB is 33 degrees. Oh my gosh. We might have fixed this. I don't know. But this is impressive. This is the best I've done so far in quite some time. The gate driver is cold, completely cold, as you'd expect. It's not driving anything. Now, while I was looking somewhere else, Oh, okay. I thought the 5 volts line just went a bit haywire, but it's my old meter here, unfortunately. Yeah, it's very old. And I'm assuming without power factor correction that 300 degrees is probably fine. The oscilloscope is wired to the gate driver output. Let's see if it switches. 3, 2, 1, go. No.
Oh, okay. What's happening? Now, I'm not entirely sure whether this is happening because the MOSFETs are not there and plus another component, or maybe the controller is faulty. After all, the Zener diode went up in smoke, the gate driver went up in smoke, and that's probably because the 12 volts line went much higher than 12 volts, than 15 volts actually. So chances are that the controller is also faulty. But fear not, because I was kind of expecting that, and I've also ordered some controllers. So if that is not working, well, I have some spares. For now, I think I'd like to just reconnect the MOSFETs and see if by any chance everything works, and if it doesn't, I'll go ahead and swap the controller as well. In 3, 2, 1, go. It's still not switching, we still have 300 volts. Everything else is fine. Well, I think temperatures are fine because the highest is 34 degrees. But I don't see switching, and obviously the voltage is not correct. So now I'm wondering whether the controller is bad or I just need to turn it on. Because if you remember, this power supply has a global on-off, and these are the 2 wires here. Another option is that this is totally normal without modules connected. So I feel that the next step would be to plug the modules back and see if that makes any difference. I got the 3 modules, 2 are 12 volts, 1 is 24 volts, and that one should be the fan controller module, back to the main PCB, and well, we'll see what happens. I guess if we don't get smoke, it's definitely a step forward. Everything is as before, but the fluke, which is reading the 12 volts line. I feel kind of optimistic. Let's give it a go. 3, 2, 1, go. No. Oh, it's even lower than before. We have 2 volts output. And most importantly, the PFC is not switching. I don't know, it could be anything to be honest, but I'd be tempted to just swap the controller. Power up, 3, 2, 1, go. No, still not working. Moo. Alright, so I didn't realize that my current limiter was limiting a bit, so that's why we didn't get 340 volts. But 340 volts, once again, is without power factor. Otherwise, we would get something like 390 volts. The current limiter is not limiting anymore, but it's still not working. Alright, I've been studying the situation here a bit, and I might have found something. Looking at the datasheet, I found exactly how the global inhibit works, and apparently there are 2 models of this power supply. One which basically works as in, if you don't connect anything to the global inhibit, the power supply just runs. If you want to turn it off, you have to do something. And then there's another model, which is the other way around. So unless you do something to the global inhibit, the power supply doesn't do anything. Now, the global inhibit is one of these optocouplers. The datasheet explains exactly what to do. You need to get the 5 volt standby out of the power supply itself, through an 800 ohm resistor, through a switch, back into the, I think it's the anode of the optocoupler, and then out of the optocoupler, the cathode pin of the global inhibit, which then goes back to the return pin of the 5 volt standby. That way, when you flip the switch, you're basically turning on the LED. You have a small resistor to limit the current, and that should trigger this section here, which should be in control of the, turning on the power supply and turning it off. What I've done, I have wired exactly as the manual says. I got 5 volts, the blue wire coming into I didn't have an 800 ohms, I have 125, so I hope it's fine, through a switch, and then back into the cathode of the global inhibit. And the global inhibit comes back through the red wire and into the yellow wire, which is the return of the 5 volt standby. So in theory, if I flip the switch, I trigger the logic. Is that gonna work? Well, we need to test that. Right, let's turn on the power supply. 3, 2, 1, go. and we are back to where we were before, so nothing really is happening. Let's trigger the global inhibit and see if it works. 3, 2, 1, go. Look at that, it's working! It's working, but the power factor corrector is not working. We got 12 volts, but without the power factor corrector. But this is amazing! We got 12 volts out of this thing, and there's nothing, I think, burning. This is an amazing result. I'm so happy, even though it's kind of half working. But this is just amazing. And also 24 volts is working. What is not working is the fan. It should really work every time the power supply is running. Alright, I think this video is getting long enough, so I think I'd like to pause it for now. Now, while I was reviewing the footage yesterday, I realized that we previously had the power factor signal coming from the controller. We probed pin number 2, and we had switching. It's just the gate driver was shorted internally and it wasn't working. But now the signal is gone. I completely forgot about that, because you see this video in like 40-45 minutes, but this power supply has been on and off on my desk for a few weeks now. So I'm not entirely sure of what happened, but I don't feel too pessimistic about the PFC circuit, because I feel it's completely independent from the logic of the PCB, and it probably takes a little bit of poking around and finding out why the controller is not outputting a signal. But that is going to require a little bit of time, so maybe that's for a part 2, assuming there will be a part 2. The other thing is the fan which was not working. Now, I tested the fan with my power supply, and the fan works. So what I did yesterday, and thankfully I had the camera switched on, because, sometimes I have these bad feelings. I thought, let's use the fan control board from the other power supply. I appreciate it's a faulty power supply, but I thought maybe that's working. And that would tell me whether the issue is with the logic on this section of the board or on the fan board itself. So I removed the fan board, which was originally installed here, installed the other one, I turn it on. Oh, fuck. Oh, no. And yes, unfortunately, something smoked out of this card, and I don't know whether maybe it was smoking before and it just kept smoking, or maybe there's something wrong with this PCB here, which is sending some voltages or so. I have no idea. Now, unfortunately, without schematics now, things are getting a bit complicated. But the massive achievement we did with this power supply is we had 12 volts and 24 volts out of it. And this is something I really wasn't expecting to see, so this is almost fixed. So we have to fix this power supply, and I'm pretty happy with it. I hope you enjoyed this video too. As usual, as I said earlier on in the video, if you enjoyed this video, please consider subscribing to this channel if you like this kind of things. Remember, I'm on Patreon. There is a free tier on Patreon. If you don't want to support me on Patreon, maybe you can buy me a coffee. But anything you can do in terms of liking the video, leaving a comment, having some sort of interaction with the video, with me, with the viewers, it really helps my motivation. Because again, it takes quite some time to shoot these videos and a lot of time to put them together. It's not an easy thing. It doesn't take me 45 minutes, unfortunately. So I guess that's it for today. I wish you a great day and hope to see you again soon here on my channels for my next videos. Thank you very much and goodbye. Bye-bye.